Hey everyone, and welcome back to the channel. Can I ask you a quick favor before we dive in? If you're enjoying our journey into the quantum world today, please hit that like button and subscribe to join our growing community of reality explorers. And here's something fun. In the comments below, tell me where you're watching from and what time it is there right now. I love seeing how our curious community spans the globe. Now, let's get to one of the most mind-bending ideas in all of physics. Picture this: you're about to make a decision. A simple choice, really, left or right, yes or no. But what if I told you that the choice you're about to make could actually rewrite what already happened? What if your decision in this very moment could reach backwards through time and change an event that technically already occurred? This isn't the plot of a new science fiction movie, my friends. This is exactly what the delayed choice quantum eraser experiment seems to suggest at first glance. When physicists first saw the results, they had to pick their jaws up off the floor. The data appeared to show that measurements made in the present could influence events that should have been set in stone billions of years in the past. The future seemed to be reaching back and whispering to the past, "Hey, let's try it this way instead." Today, we're going to unpack one of quantum mechanics' greatest puzzles, the so-called reality rewind button. We'll explore those baffling anomalous results, visualize how information seems to reach backwards to dictate quantum states that should already be determined, and sit together in that wonderful moment where we ask the million-dollar question: how can knowledge from the future change what already happened? But here's the real twist. By the end of our journey, you'll discover that what initially looks like time travel might be teaching us something even stranger about the nature of reality itself. So, get comfortable, open your mind, and let's dive down the quantum rabbit hole together. When physicists first conceived of what we now call the delayed choice quantum eraser, they knew they were playing with some pretty wild ideas. The brilliant mind of John Archibald Wheeler first proposed this as a thought experiment in the late 1970s. And he framed it in the most dramatic way possible, on a cosmic scale. Wheeler asked us to imagine light from a distant quasar, a tremendously powerful cosmic beacon billions of light years away. This light travels through the universe for eons, and on its journey, it passes by a massive galaxy that bends its path through what we call gravitational lensing. Essentially, the light can take two different paths around the galaxy, just like a photon might go through two different slits in a laboratory experiment. Now, here's where it gets truly mind-bending. After this light has been traveling for billions of years, when it finally arrives at Earth, physicists can choose how to measure it. They can set up their detectors to determine which path the photon took, treating it like a particle that chose one specific route. Or they can set up their equipment to allow the two paths to interfere with each other, revealing the photon's wave-like nature. The stunning implication seems to be that the decision made by physicists today, billions of years after the photon began its journey, determines whether that photon traveled through the universe as a particle following a specific path or as a wave exploring all possible paths simultaneously. Wheeler's provocative conclusion was that the past has no existence except as it is recorded in the present. Let that sink in for a moment. He's suggesting that history isn't fixed until it's observed, that reality doesn't become real until it's measured. This isn't just poetic philosophy, it emerges directly from the mathematics of quantum mechanics. Now you might be thinking, sure, that's a fascinating thought experiment with distant quasars, but what about actual laboratory evidence? Well, by the 1980s and 1990s, technology had advanced enough to test these ideas right here on Earth. In 1999, a groundbreaking experiment led by Yoon-Ho Kim provided stunning confirmation of Wheeler's intuitions, but with an important twist that we'll explore throughout this video. In Kim's experiment, they didn't use light from distant quasars, they created their own photons in the laboratory. They'd send a photon toward a double-slit apparatus, but then they'd use a special crystal to split each photon into two entangled photons after it passed through the slits. One photon, called the signal photon, would travel straight to a detector screen. The other, called the idler photon, would take a much longer path through a series of mirrors and beam splitters before finally arriving at one of several possible detectors. The crucial point is that the idler photon would arrive at its final detector significantly after the signal photon had already been detected. Now, here comes what seems like pure magic. Depending on how the experimenters set up the detectors for the either photon, specifically, whether they measured it in a way that preserved which way information or in a way that erased that information, the pattern formed by its entangled partner, the signal photon that had already been detected, would be different. It appeared that a measurement choice made after the signal photon had already been recorded was determining whether that signal photon had behaved like a wave or a particle. Let that sink in for a moment. The signal photon hits its detector. Its fate is sealed. Its position is recorded. Then, nanoseconds later, which is an eternity in quantum terms, its entangled partner arrives at a different set of detectors, and the choice of how to measure that partner seems to rewrite the history of the signal photon that's already been detected. If that doesn't make your brain do backflips, you might not have fully grasped the implications. This brings us to what I call the immediate moment, that point where your intuition about how reality works completely shatters. How can future knowledge change what already happened? Our everyday experience tells us that the past is fixed and immutable. If you burned your toast this morning, that's it, it's burned. No future decision can change that fact. The toast is burned, and it will always have been burned. But in the quantum realm, the delayed choice eraser experiment seems to suggest that until we make a specific measurement, certain aspects of the past might not be fully determined. This apparent retrocausality, where future events seem to influence past events, represents one of the most profound puzzles in all of physics. But here's where I need to let you in on a little secret that many popular science explanations gloss over. The reality is more nuanced, and arguably even stranger than simple retrocausality. As one analysis puts it, the delayed choice quantum eraser experiment does not rewrite the past, despite what numerous videos and articles might claim. What's actually happening has more to do with quantum correlations and how we interpret data than with genuine time travel. But to understand why, we need to go back to basics and build our understanding from the ground up. To truly appreciate the quantum eraser, we first need to revisit one of the most famous experiments in all of physics, the double-slit experiment. This beautiful, simple experiment reveals the very heart of quantum weirdness, and it's where our story really begins. Imagine a wall with two thin, parallel slits cut into it. On one side of this wall, we have a source that can fire particles, let's say electrons, one at a time toward the slits. Behind the wall, we have a phosphorescent screen that lights up wherever an electron hits it. This is exactly the setup that physicists use in laboratories around the world. Now, if we were firing tiny bullets at this wall, we'd expect to see two distinct bands on the screen behind, one band behind each slit, where the bullets had passed through. But with electrons, something very different happens. As we fire electron after electron, a pattern slowly emerges on the screen, a series of bright and dark bands called an interference pattern. The brightest band is right in the middle, directly between where the two slits are, with alternating dark and bright regions spreading out to either side. This is exactly the pattern we would expect if we were dealing with waves rather than particles. Think of water waves approaching a barrier with two openings. The waves spread out through both openings and then interfere with each other. Where crest meets crest, they reinforce each other and create a bigger wave. Where crest meets trough, they cancel each other out. The interference pattern of bright and dark bands on the screen is the unmistakable signature of wave behavior. Here's what makes this truly quantum. We're sending these electrons through one at a time. That means each electron is essentially interfering with itself. It's as if each individual electron is passing through both slits simultaneously, like a wave, and then interfering with itself on the other side. This is where we get the idea that quantum objects exist in a superposition of states. They're simultaneously taking multiple paths until they're measured. But the weirdness doesn't stop there. What happens if we try to determine which slit each electron actually goes through? If we place a detector at the slits to monitor which path each electron takes, something remarkable happens. The interference pattern disappears. Instead of the beautiful banded pattern, we just get two blurred clusters, one behind each slit. The very act of measuring which path the electron takes seems to force it to choose a definite path, collapsing its wave-like nature into particle-like behavior. This is the quantum version of peaking ruins the magic. The electrons seem to know whether we're watching them or not. When we don't monitor their path, they act like waves exploring all possibilities. When we do monitor their path, they act like well-behaved particles following a single trajectory. This complementarity between wave-like and particle-like behavior is fundamental to quantum mechanics. We can observe one aspect or the other, but never both simultaneously. The which way information and the interference pattern are complementary observables. Knowing one destroys our ability to see the other. Now, here's where we set the stage for our crucial twist. For decades, physicists assumed that this loss of interference was permanent. Once you gained which-way information, the interference was gone for good. The quantum cat was out of the bag, so to speak. But in the 1980s, physicists began to wonder, what if we could somehow erase that which-way information after the fact? What if we could, in a sense, unlearn which path the particle took and recover the lost interference pattern? This brilliant insight, that we might be able to undo the effects of measurement, set the stage for one of the most clever experiments ever conceived, the quantum eraser. Now we arrive at the heart of our mystery, the quantum eraser itself. This ingenious experiment takes the double-slit setup and adds a fascinating twist that seems to bend the rules of causality itself. The fundamental idea behind the quantum eraser was first proposed by physicists Marlon Scully and Kai Drull in 1982. They realized that if which-path information is what destroys interference, then perhaps interference could be recovered by erasing that information after the particles had already been detected. It's like having a cosmic undo button for quantum measurements. But how do you erase information that's already been recorded? This is where quantum entanglement comes into play, what Einstein famously called spooky action at a distance. In the actual experimental realization by Kim and colleagues in 1999, they used a clever trick involving entangled photons. Here's how it worked. After a photon passed through the double slits, it would encounter a special crystal that performed what's called parametric down conversion. This crystal had a remarkable property. It could take one incoming photon and convert it into two entangled photons, each with half the energy of the original. So now, instead of one photon, they had a pair of entangled photons, twins quantumly connected to each other. As we've seen, the quantum eraser doesn't actually allow us to rewrite history, but it does open extraordinary windows into the deep structure of reality. Its implications extend far beyond philosophical puzzles, influencing cutting-edge technologies like quantum computing and inviting us to reconsider fundamental concepts like information and time. In the world of quantum computing, the principles demonstrated by the quantum eraser are absolutely crucial. Quantum computers rely on maintaining superpositions of states, allowing quantum bits, or qubits, to explore multiple possibilities simultaneously. But these fragile superpositions can easily be destroyed by decoherence, which is essentially the environment measuring the quantum system. The quantum eraser teaches us that it's not the physical interaction itself that destroys quantum behavior, it's the potential for information about the system to leak into the environment. This insight is guiding researchers as they work to protect quantum states from decoherence. By controlling and limiting the flow of information, we can preserve quantum effects for longer periods, making more powerful quantum computation possible. In quantum information theory more broadly, the eraser experiment highlights a profound truth. Information is not just an abstract concept, it has physical consequences. The presence or absence of information literally changes how physical systems behave. When which-path information exists somewhere in the universe, photons behave like particles. When that information is erased, the same photons behave like waves. This suggests that information is a fundamental aspect of physical reality, not just a human abstraction. This connects to what many physicists see as one of the most important unresolved questions in fundamental physics. What does erasing information truly mean at the quantum level? When we talk about erasing which-path information, we're not just talking about deleting a file from a computer or forgetting something we once knew. We're talking about a physical process that systematically destroys the possibility of ever knowing which path was taken. In the quantum eraser experiment, this erasure isn't done by simply ignoring information, it's done by combining beams in such a way that the path information becomes fundamentally unknowable. The paths are mixed at a quantum level, making it impossible even in principle to determine which path was taken. This active, physical process of information destruction is what allows quantum interference to reappear. But here's a fascinating subtlety: the interference doesn't actually come back in the main data set. It only appears when we selectively look at subsets of the data. This has led to ongoing debates about what quantum erasure really accomplishes. Some physicists argue that since the interference is only visible in post-selected data, the erasure is really just a sophisticated form of data analysis. Others maintain that the recovery of interference, even in selected data, reveals something deep about quantum reality. This debate addresses one of the most profound questions in the interpretation of quantum mechanics. Are quantum states real physical entities, or are they merely representations of our knowledge? If quantum states are real, then the erasure genuinely changes something physical about the system. However, if quantum states merely represent what we know, then the erasure is essentially about updating our information. Most physicists today take a middle road. Quantum states have elements of both reality and knowledge. They're not completely independent of what we know, but they're not merely subjective either. The quantum eraser sits right in the middle of this tension, showing how our knowledge and physical reality are deeply intertwined in the quantum realm. Looking beyond these interpretational questions, the quantum eraser continues to inspire new experiments and technologies. Researchers are now developing more sophisticated versions of quantum erasure that could lead to better quantum sensors, more secure quantum communication, and deeper tests of quantum foundations. For instance, some recent experiments have explored quantum erasure with massive particles, not just photons, pushing the boundaries of how large an object can display quantum behavior. Others have tested erasure over increasingly large distances, probing whether quantum effects can be maintained across kilometers or even between satellites in space. The quantum eraser has also become a testing ground for alternative interpretations of quantum mechanics. From the many worlds interpretation to cubism to relational quantum mechanics, each interpretation offers a different perspective on what's happening during quantum erasure. By refining these experiments, physicists hope to distinguish between these competing views of reality. But perhaps the most beautiful lesson of the quantum eraser is this: our universe continues to surprise and challenge us. Just when we think we understand the rules, quantum mechanics reveals another layer of mystery. The eraser experiment takes what we thought was settled, that measurements are irreversible, and shows us that at the quantum level, even the distinction between past and present is more fluid than we imagined. Most physicists today take a middle road. Quantum states have elements of both reality and knowledge. They're not completely independent of what we know, but they're not merely subjective either. The quantum eraser sits right in the middle of this tension, showing how our knowledge and physical reality are deeply intertwined in the quantum realm. Looking beyond these interpretational questions, the quantum eraser continues to inspire new experiments and technologies. Researchers are now developing more sophisticated versions of quantum erasure that could lead to better quantum sensors, more secure quantum communication, and deeper tests of quantum foundations. For instance, some recent experiments have explored quantum erasure with massive particles, not just photons, pushing the boundaries of how large an object can display quantum behavior. Others have tested erasure over increasingly large distances, probing whether quantum effects can be maintained across kilometers or even between satellites in space. The quantum eraser has also become a testing ground for alternative interpretations of quantum mechanics. From the many worlds interpretation to cubism to relational quantum mechanics, each interpretation offers a different perspective on what's happening during quantum erasure. By refining these experiments, physicists hope to distinguish between these competing views of reality. But perhaps the most beautiful lesson of the quantum eraser is this: our universe continues to surprise and challenge us. Just when we think we understand the rules, quantum mechanics reveals another layer of mystery. The eraser experiment takes what we thought was settled, that measurements are irreversible, and shows us that at the quantum level, even the distinction between past and present is more fluid than we imagined. The universe is stranger than we can suppose, but it's not arbitrary. It follows elegant mathematical rules, even if those rules conflict with our everyday intuition. The quantum eraser doesn't break the rules of quantum mechanics, it emerges naturally from them. The surprise isn't that quantum mechanics is wrong, but that it's even more subtle and fascinating than we initially realized. As we continue to probe these quantum mysteries, we're not just learning about photons and slits, we're learning about the fabric of reality itself. Each experiment, each paradox, each moment of confusion brings us closer to understanding our place in this strange and wonderful quantum universe. And there you have it, friends, the quantum eraser in all its mind-bending glory. What initially looks like a reality rewind button turns out to be something both more subtle and more profound, a reminder that the universe operates according to rules that constantly challenge our intuition. As we've journeyed together from the basic double-slit experiment through the intricacies of quantum entanglement and information erasure, I hope you've come to appreciate both the mystery and the elegance of our quantum reality. The universe is under no obligation to make sense to us, and yet, through patient experimentation and creative thinking, we gradually untangle its beautiful complexities. If you've enjoyed this deep dive into the quantum eraser, I'd really appreciate it if you'd hit that like button and subscribe to Happy Sleep for more journeys to the edge of understanding. And remember, I'd love to know where in the world you're joining me from and what time it is there, so please leave a comment with your location and current time. As for me, it's getting late here, and I've got more quantum mysteries to explore. So, from all of us here at Happy Sleep, good night, wherever and whenever you are. May your dreams be as expansive as the quantum wave function, and may you always remain curious about this astonishing universe we call home.